Hi folks, welcome to the next chapter regarding understanding uniaxial stress. So today we're looking at parts that relates to shear stresses. Shear stresses can be a very extensive topic, but we're going to first start off by looking at the fundamentals relating to what shear stresses are. So let's do a very quick recap in terms of what's been covered today. So we first started looking at chapter 1 to 3, where we talked about failure in engineering materials, so things like brittle failure, ductile failure, creep, fatigue. So we looked at that. Then we progressed to look at the concept of calculating for stress and strain. And we progressed to look at what is termed the Young's modulus or the elastic modulus, and how to go about deducing or measuring the measure of energy that causes a component to deform. So that's basically the strain energy. We then looked at, in terms of chapter 4, thermal loads, so how temperatures can more or less cause components to deform. So we looked at that under chapter 4. And the last bit that we looked at following thermal loads regarded the concept of compatibility. So if we had a situation whereby there is some measure of indeterminacy, how do we go about solving such a problem? So where we have a situation where the materials might be different, or there might be some sectional change in the component along its axis, how do we go about calculating or predicting the stress and the strain, or the measure of deformation, based on certain equations that we can use to overcome such problems? So we're now going to focus on shear stresses. So what are shear stresses, and how does that relate to deformation in materials? So before we look at shear stresses in a bit more detail, we need to think about what shear forces constitute. Over the past couple of chapters, we've looked at situations where the applied force is coaxial to the center line or the axis of a given component. So what if we have a situation whereby the applied load is offset? So it is collinear in terms of the plane of deformation. However, the force is at an offset to the central axis as shown in the diagram. So due to this fact, the reaction with respect to the applied force will cause the component to distort. This is essentially what denotes the shear force. So I've defined the shear force as follows. So the shear force, or the shear forces, which is normally characterized by the letter capital V, transpires when the forces acting on the component or material are offset to the neutral axis, as shown in the diagram. Opposite direction, so again, looking at Newton's third law, so when you have forces that are equal, but the centers are more or less acting in opposite directions, then that's essentially what shear forces more or less characterizes. And it's tangential, so the force is tangential or parallel to the cross-sectional area of the given component, as shown in the diagram. The next diagram looks at what is the nature of deformation. So if you look at this diagram here, you realize, right, that the point of application of the force will displace a distance. So here, let's assume that that distance is AB. And that will cause some measure of angular deflection. And it's this angular deflection that causes distortion in the component. So unlike axial stresses or loads that are applied axially, where we don't see this measure of distortion, we just see some measure of extension in the component's length or some measure of reduction in the component's length. When it comes to shear forces, due to the offset of the forces to the neutral axis, you get this angular distortion. And this is the type of loading that causes volumetric distortions in components. Before we look at the various formulae relating to calculating the magnitude of the shear stress due to the applied shear force, the measure of the distortion experienced by the component, aka the shear strain, and what the ratio of the stress to the strain is in terms of the Young's modulus equivalent, let's look at the nature of the shear variation due to the applied shear force across the cross-sectional profile of the given component. If we have a situation, as shown in the diagram, where an applied shear force is causing a component to distort, and the shear force is parallel to the neutral axis or the center line of the component, I like to call the center line the axis or plane of shear. We'll realize that the greater the offset between the shear force and the axis of shear, the greater the shear will be along the center line. So as a result, an equivalent shear force reaction is experienced along the center line or the shear plane of the component. Thus, over time, distortion will be induced in the component, which will eventually cause the component to shear or fail. So from the shear variation diagram, we realize that the maximum shear stress experienced by the component, and the maximum shear stress is denoted by the notation tau. The maximum shear stress will be experienced at the plane of shear of the component. So this leads us to looking at the various equations for us to calculate shear stress. So this diagram is just a large and enlarged view of the diagram that we just looked at. So to calculate the shear stress, so as I've more or less inferred, shear stress is denoted by the Greek letter tau, to differentiate that from axial stress, which is denoted by the letter sigma. So tau is equal to V, so V is the shear force, not the axial force, divided by the tangential cross-sectional area of the given component. To calculate the measure of deformation, so in this instance, that measure of deformation or that measure of distortion is denoted by the term shear strain, and that's represented by the Greek letter gamma to differentiate shear strain from axial strain, which is denoted by the Greek letter epsilon. Gamma is equal to delta L divided by W, or the ratio of delta L divided by W. So what is delta L? So delta L in this instance, when it comes to understanding shear stress, does not necessarily denote extension, as we've more or less looked at under uniaxial stress. Here we can term delta L as the measure of displacement of the applied shear stress, the applied shear force on the given component. So that measure of displacement experienced by the component, which will cause the component to distort, that's essentially delta L. And W represents the span of the component, which is normal to delta L. If we look at this diagram very carefully, you realize that the profile formed by W and delta L is that of a right angled triangle. Thus, we could say that the tangent of gamma is equal to the ratio of delta L over W. Similar to uniaxial strain, shear strain doesn't necessarily have any dimensions. However, because we're looking at angular distortion or angular deflection, we could represent or denote the unit for gamma in terms of radian. So again, it's more or less up to you whether you want to denote the unit for shear strain as dimensionless or denote the measure of shear strain in terms of radian. Okay, so radian, that will be spelled R-A-D-I-A-N, in short R-A-D or rad. So we have to be very careful that we don't express gamma as a degree. What you have to do is you calculate for gamma and you convert from radians to degrees. So we'll look at similar situations when we go through our work along series relating to shear stress. And the final equation that we're going to be looking at will be the shear modulus. And the shear modulus is denoted by the letter capital G, and that's equal to the ratio of the shear stress to the shear strain. And there we have it. So this is equivalent to what we have in terms of predicting the resilience of a given material. So this is known as the shear resilience, or the modulus of rigidity. So as a rule of thumb, in terms of how G relates to E, so E, don't forget, that characterizes the elastic modulus, we could say that G is approximately equal to about 38 to 40% of E. So now let's look at the effects of shear with respect to components subjected to a tensile load and the situation whereby a component is subjected to a shear force. So in this diagram here, you've got a fastener that's been subjected to a force Ft, and Ft is coaxial to the center line of the given component. Now, as the component stretches, you realize that, particularly with ductile materials, you have what's called localized necking, and this is due to a lateral strain that is causing some shear effect, which will eventually cause the bolt to break or cut. If we look at this diagram here, you've got the plane of shear, and with respect to the plane of shear, we realize that the applied load has some considerable distance from the axis of shear. And the greater the load is, or the longer this load is applied, over time, the component of the bolt will undergo significant distortion to eventually fails and shears along XX, or the axis of shear. And as designers, it's very important that when we are analyzing components, we need to ensure that we also look at the effects of shear, because it's shear that causes failure in components at least 70+% of the time. Okay, so when you're designing components, you need to ensure that you design in such a way that you design components to resist the effects of shearing, which will cause significant distortion and failure in components. Alright, so let's look at typical situations where components could experience some measure of shear stress, which will lead to eventual failure. So in the given diagram, we have a bolt which is clamping two plates of material together. The interface of the two plates creates a single axis of shear, and this is where it's likely to cause deformation or shearing across the cross section of the given bolt in the diagram. So this configuration provides a single shear plane. Thus, in calculating the shear stress experienced at the cross section of the bolt due to the applied shear force, then we can go on to say that tau subscript SS, so SS characterizes or denotes single shear, that's equal to the shear force divided by the cross-sectional area. This is basically what's happening here. Okay, so this is fairly straightforward. So let's look at what double shearing constitutes. So unlike the previous example whereby the interface of the plates creates a single axis of shearing, if we have a situation whereby we've got three plates clamped together by a bolt, the two interfaces created by the intermediate plate and the adjacent plates creates 2 points of shearing across the cross section of the bolt. So plate 1 and plate 2 creates an axis of shear x1, x1, and the contact between the intermediate plate and plate 3, if you want to call it that, creates a cutting plane x2, x2, as shown in this diagram here. Now, to keep this system in equilibrium, the force experienced, or the shear force experienced by the intermediate plate, should be equal to the sum of the forces experienced, or the reaction experienced by the outer plates. Okay? Thus, in calculating for double shear, so double shear, that is represented by the subscript ds. So tau ds is equal to half okay, because we're looking at the shear at each interface, okay. So that'll be half V divided by A. And because 2 is the denominator, that then transposes to give V over 2A. So it's very important because the load, okay, will not be at one single point, unlike the single shear. It will be half that load at each interface, okay, of the plane of cut. Okay, so we need to really bear that in mind.
Alright folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.